Welcome everyone. Thanks a lot for attending our talk titled Rotation Sensing Using Passive RFID Tags. I am Swadhin Pradhan. I'll be presenting this talk on behalf of my co-author, Lili and Lili. This was a work which has been done in UT Austin as a last problem I kind of solved for my dissertation. So I'm currently working as a engineer with Cisco Meraki, but I'm happy to present this interesting work to you. So one thing is for sure, sports analytics as an industry is growing really fast. So the information needed to analyze the performance of a sports person is very critical to improve their performance. So it has been estimated that by year 2024, it would become a 5.2 billion industry, which is already around 2 billion currently. And this is true across all the region, including Europe, America, and Asia. So in sports analytics, there are different kinds of motion. So, but one of the interesting motion we can look at is ball motion information. So we can use that to provide different kinds of analytics in bat or ball sports. So there's batter ball sports. Examples are baseball, cricket, basketball. We can look at the motion of the ball of different sizes here to know how the player is performing. And this can be used for coaching and performance improvement. We can provide personalized coaching service to a expert or a naive player by doing this. And this ball motion has different component. One is very straightforward linear speed and direction. So another two is a little interesting, which is very important in baseball for pitch action, or cricket where the ball is played, is the rotation speed, that how the ball is rotating and the rotation direction, and also which axis it is rotating. Interestingly, there have been many work in tracking the ball motion, but there are very fewer which is used in estimating rotation speed and direction, rotation axis in a easy way. So in this paper, our primary focus is to get this information without instrumenting the ball or changing the environment drastically. So what are the current approaches to get this information? One is high-speed camera, which is kind of already being used in both cricket, soccer, and American football. But the issue is it does not work in non-line of sight, and the cost is very high, around $1 million. And there are also inertial measurement unit-based approaches, but it requires non-trivial modification of ball, and some of them also needs battery, so there is a need of constant change. So another approach in a research domain is Wi-Fi and Bluetooth beacon-based approaches, where you have antenna array of Wi-Fi or Bluetooth, and the ball contains the beacon which sends the signal at a particular time interval, and we can estimate the ball location using angle of arrival estimation and the distance estimation through time of flight calculation. But for this, we need very accurate specific calibration because we need to get perfect localization of the ball. And the ball and this solution also need a battery, and there is a non-trivial modification both in ball and the playing conditions, because you require a huge set of antenna array. So in this paper, we try to get those information without these costly or highly modifying approaches. We ask that can we detect the rotation motion with minimal change using passive RFID tags and a single reader antenna. So if you impose a single antenna setup, which is also commercial of the self, it becomes very easy to deploy. And we are selecting passive RFID tags because it has a very low physical footprint, and also it does not require a active battery. So we don't need to change the battery very frequently. So can we use those tags and attach them to the ball and get the information at the reader's type through a single antenna and estimate the rotation and other related motion with minimal change? And the answer is yes. In a limited condition with a certain range, we can get an accurate rotation estimation with a related motion information, which can provide rich analytics to the sports domain if we exploit the polarization property of a passive RFID tag. So by polarization, I mean the electromagnetic field angle which has been created while interacting with this kind of passive RFID system. So here I will kind of go over the key idea, algorithm, and evaluation by following this pipeline. So as I said, our key idea is to exploit the polarization property of the RFID tag with a linearly polarized antenna. The tag is also linearly polarized, that it can be recorded in a certain planar electromagnetic field, and we can estimate the location of the tag used by exploiting that. Because the phase of the RFID tag theta and the received power P received is a function of the distance, the polarization, which is gamma, and also the gain of the antenna. So for a given distance, if we know the gain pattern of the antenna, we can get the phase which has been captured through the polarization change, and which is also a function also with the relative angle of the particular tag attached to the ball. And from those information, we can extract the motion states of the ball using just a single antenna. And the key idea roadmap, which I'll explain more in the coming algorithm section, and also you can get a bigger detail in the paper. So the key steps are the following. We first model the RSS and the phase under rotation. Then we get the estimation of the rotation axis, which is the angle of the axis with the X, Y, and Z axis through an optimization framework. We also include the azimuth and the elevation corresponding to the reader antenna. And then we get those information, but as you can already guess, the major challenge is that that optimization framework becomes non-convex, and there is issue in the initialization. we solved that problem, and the details are in the paper, but I can also go over those things a little later. In using three things, we use multiple tags, namely three tags on the ball itself. We leverage a specific neural network design for modeling and estimating the initialized solution. And we also exploit the temporal locality of the ball motion, because a motion n is a function of motion n minus 1 in the free air if you don't interact with any other motion while ball going over the air. And then after estimating the rotation axis and the azimuth and the elevation, we extract the translation by the relative slope change of the phase. So that is the linear motion. So we simultaneously get the rotational linear motion from the RF signal itself. And as I said, the key idea roadmap are like this, and I can go a little deeper on each of the things. As I said, we use a modeling parameter, which is the phase and the RSS, which is a function of the distance, polarization, and the gamma and the gain of the reader and the tag. And if we model them after getting the polarization constant of the k, which is corresponding to a particular tag, and if we select the frequency, and if we get the gain pattern of the antenna and sample them correctly, we can model them very accurately. And we see, and which is borrowed from the literature, we see the modeling at different angles. Here, the 0030 and 45020 means the relative angle with different axes. The red curve represents the change of the actual result for a given pattern. And the blue curve represents the analytical model, which we get from the previous modeling. And see, there is a huge similarity between this pattern. And also this is true for the phase. So, and for another interesting observation, you can see, so for different rotation axis, we can get almost the unique pattern. So if we can have these patterns getting from RSS and the phase, we can estimate the corresponding rotation axis. And we also see for different direct or indirect multipath creation, the pattern or different configuration remains similar, and the shape, specifically the shape, remains similar. Therefore, we can use that for a estimation purpose, reversely mapping them to the rotation axis. And this is our optimization framework, where MK is the model, and θ1, θ3 is the rotation axis, and RKI is the sample signal. We minimize with θ1, θ2, θ3, and we get the corresponding value. And we also extend to include azimuth and elevation by adding two more parameters to the same optimization framework when it is not in a single, in a static azimuth and elevation location. However, as you can see, this is a nonlinear optimization and non-convex, and there is an issue that the initialization can matter to get a very accurate estimation of the rotation axis. We use a neural network driven initialization technique. The details are in the paper, but the key idea is the following. We use a multi-layer feed-forward neural net with a 4-layer with different number of neurons, where we map the phase and RSS to the rotation axis 3 angle and later azimuth and elevation. And we get the training data from the measurement and also our synthetically generated analytical data, and we augment the data by perturbing the output of the rotation axis, making the initial also the input same. So we get a very accurately trained neural network for this particular model. And as you can see that the increase of layer after 5 does not change that much. The mean angle error is the y-axis. And as I said, not just DNN, if you can include the temporal locality, that is the estimation, we'll select theta 1, theta 3, theta 3 in T1, T2, where the change is minimal because there is should not be any drastic change going from state T1 to T1 plus 1. And from the CDF in the right hand side, as you can see, the angle error reduces from 30, median error reduces from 32 degree to 9 degree and to 5 degree. So we can get a very accurate estimation system through our optimization framework and model. And after estimating the rotation axis, we get the rotation speed by counting peak to peak distance, which is how many peaks we are getting, where 2 troughs and 1 peak, and or 2 peaks and 1 trough consisting of a 1 full rotation, and we count that from the RSS pattern to get the rotation speed. Then we get the linear speed by extracting and compensating for the rotation axis and the rotation speed, and to get the slope of the change of the phase, and from that we can get the distance traveled, and therefore for a given duration we can estimate also the linear speed. Details are in the paper. I would encourage you to see that. So overall, the algorithm looks like this. We first create a denoised RSS and phase trend from the RFID tags, which is attached to the ball. And we detect the peak and valley from the RSS pattern. And we create the RSS and phase template for a given rotation. And from the optimization framework, we estimate the rotation axis, the rotation speed, and azimuth and elevation. First, we get the axis, azimuth, and elevation, and then we get the speed. And after we estimate the phase compensation on that, we get the linear speed, distance travel, and the direction from the phase trend, and the total change, and the phase slope. So we'll go over a set of evaluation which we did in a control setup. So we have a linear polarized antenna, and we create a goniometer, which is 3D printed, to create different and fixed rotation where we can estimate also train our model. And we put the ball, and we attach the tag at different locations of the ball. And we also, to create a control linear motion, we use a linear guide where we connect the linear guide to a power supply and also a motor driver. And we also put the ball to create a rotation motion in a NEMA 34 motor with a driver and a power supply, and control that with the PC. So we can create a different combination of rotation motion, linear motion, and also with the rotation axis from the goniometer itself. And the length of linear glide is around 3 meters, and the speed is within around 2.5 meters per second, the highest speed. And for RPM of the motor can go up to, I guess, 600 RPM. So in this setup, we estimate the rotation axis with 1 tag and 3 tags, and with the training in one location, estimating in another location for the neural network. As we see in both of the cases, the median error remains within 5 degrees. So for the rotation axis estimation, we also change different micro benchmark experiment, we change the rotation speed of the ball and also distance from the antenna, and up to 2 meter, which we get a relatively good performance, and the error remains within 5 dB. And we are assuming in this ball motion analytics, there is a location where you put the antenna of the antenna, and we can get the information within 2 to 3 meters. And the linear distance estimation from the CDA for different speed and different distance, the error remains within 1 centimeter. And similarly for azimuth elevation, for different distances and different speed, the median error remains within 6 dB. We also perform different multi-path experiments by blocking the line of sight and also creating different indirect multi-path environment. In this setting, for different setup, we see both static and dynamic that does not degrade the performance really bad. So there are many experiments in the paper. In general, both in multipath and different configuration, the result of rotation axis, rotation speed estimation in the control setup within 3 meter, the performance remains relatively well. And to our work, there are many work which try to do ball motion analytics by using IMU, which suffers from the same issue I just mentioned before. And there is also a combining IMU and EWB ranging-based, ultra-wideband ranging-based system proposed to get the location of the ball, but it requires multiple antenna array and a hugely modified ball. So there are also RFID-based approaches, which is very close to our system, which also use RF signal extracted from the tag to estimate its location, but it's mostly static orientation, tag gyro, translation, RFI draw, and RFind, which use exact localization. Therefore, you need very high bandwidth with a modified user system. And for tag gyro, even if it uses cost system, you will require multiple antennas. So the key takeaways of our system called tag inertial measurement system, STIMU, is the following. Polarization can be exploited for motion sensing. It can sense different motion sense without tracking, because we are looking the relative motion. And this is, to the best of our knowledge, is the first RFID-based single antenna system to get the rotation motion within a relatively long range. Thank you. If you have any question, please let me know.